let's see. So today is a Legion week. I'm going to be talking this week some more about logical analysis. So, I went back and watched the recording from 3 weeks ago, and I wanted to, there's some ideas that I didn't quite get across in how logical analysis works in Legion that we're going to try and cover today. So before I start talking about those, let's just refresh, where we are, what Legion is doing. So remember that logical analysis is effectively trying to find dependencies, for every operation that you launch off, whether that's a task or an index task or copy or inline mapping or what, right? You're trying to find dependencies on the operations that came before you in the program, right? And we're trying to do this by walking the region tree, right? So remember that, maybe you have a region tree and prior operations have recorded themselves as using various other logical regions, or if they're a projection region requirement, like other partitions in this region tree, as some new operation comes in, it wants to, maybe do an index-based launch from a different partition, right? And so it'll need to, first traverse down this tree and find things that it interferes with, right? And then come back up and then go down its part of the tree and record itself so that other things that come after it can then find it as a dependence, right? And so logical analysis is effectively the process of computing those mapping dependencies, which will determine the order in which things map in the program. And it's doing this by traversing the region trees to look for prior interfering operations, whether they interfered, on regions or fields or privileges and stuff like that. And so the main method that does this, right, which we started looking at the last time, is this register logical user, right? And in fact, if I actually search for that, like up here at the top of the, top of the file, right? So, every operation will call this perform dependence analysis, right? It passes itself in, its index, its region requirement, any projection, information about whether it's doing a projection region requirement, and the path of the region tree that it's going to walk along in order to register itself, right? Especially walking from wherever its parent task had privileges down to where, it's asking for privileges in this region tree, right? And it's going to be performing a logical analysis as part of that, right? And effectively, what we do is we get the the parent node is where the parent task had privileges. So like if you actually look at where this parent node comes from, it's actually from the parent argument in the region requirement, right? It's effectively saying where that task derived its privileges from, right? So we're going to start at that point in the program, and we're going to call this register logical user, and it's a recursive method that will gradually walk down this tree, along the path to where it needs to go, but it also will traverse subtrees that are open and close them up, as necessary if there's interfering stuff in them. So what I want to do is talk a little bit more about how we do this closing, and then also some of the analysis that we do on each of these different things, because I feel like I didn't quite get across some of the more important details in the last lecture. Okay, so if we go back to register logical user, I'm going to point out here that I am, if you notice in this URL, I am in the shard refine branch. So effectively, I'm trying to show you what this code looks like, in the most recent incarnation of Legion. If you look at like the master branch and stuff, it'll look a little bit different. There's some slightly different function names, but a lot of this has been a little bit factored and cleaned up here, so it's a little bit cleaner. Right, so when you call register logical user on a particular node, right, you come in here. One of the first things that you're going to do, though, is effectively do this call siphon interfering children. And what this is doing is effectively, and we're going to go look at this method here in just a minute, but for any given node that you're at in the region tree along your path, right, effectively you're going to look for any interfering children that you might need to close up, right, and register dependencies on other operations that came in the subtree because they might be interfering with you, and you're just traversing down your path, but this subtree over here might alias with you. In this particular case, like if you have two different partitions, right, if you're traversing one partition, there may be things in that other partition over there that interfere with you that you need to close up. Right, so siphon interfering children is effectively the method does this. There's this little branch here, if unopened field mask. This is a little optimization which says, like, effectively, if we've already closed up, a particular field as we've been doing this traversal up above us, then we don't need to check for interfering children because, like, we've already done all of our closes, so we're just opening up, a new subtree. And so that allows us to elide this call to siphon interfering children in some cases. But that's a performance optimization. You could actually completely remove this branch right here and just always call siphon interfering children, and the right thing would happen. So let's go actually look at siphon interfering children here. So one of the things that's happening here, right? If I come back to this region tree, one thing that's happening is, effectively, in order to have a dependence on a prior operation, right, three things have to be true. One, you have to have interfering, or overlapping subregions, right? Effectively, you have to be, using a subregion or a partition that interferes or overlaps with another partition or region that some prior task was using, right? You have to have overlapping field sets, right? And third, you have to have like an actual dependence. Like if both of them are reading, well, then there's not going to be any interference, right? Or need a dependence between them. So all three of those things have to be true. So we're looking for like ways to avoid finding dependencies as much as possible, right? And the traversal of these region trees are effectively what's doing the spatial check, right? Checking to see whether the two regions or partitions are overlapping with each other. But if you can't prove that, well, then the next thing to look for are looking for like, are there overlapping fields? And if there's not that, then checking to see if there's like non-interfering privileges, like both of them are reading or both of them are reducing with the same reduction op, right? And so what we're trying to do is effectively rule out as many things as we can. But if we're forced to record a dependence, then that's what we're going to do, right? And so effectively this first check on siphon interfering children is just looking to see like like are there any are the subtrees even interfering with us or overlapping with us? And then if not, like looking for, do they have only things in disjoint sets of fields from us, or are they using only things like reading down in this part in this subtree, so we don't have to traverse it because we're just going to be reading over here, right? So siphon interfering children is going to be looking for all three of these conditions and trying to, as soon as it finds one that is non-interfering, then we get to move on and go to the next thing, right? Okay. So how does this siphon interfering children work? Well, there's an important data structure that we track on every node in this region tree, and that is this field states data structure. So if we go to look at field states, that's actually defined in Legion analysis .h right here. Right. So field state is effectively tracking, for every node in this region tree, it's tracking which children are open and what mode are they open in. And so what we're actually, showing here is we're tracking a group of open children, and that's just like, names of immediate children in the region tree. So like, for example, like for this node right here, it has two immediate children, has a partition here and a partition here. And for this node in the region tree, which is a partition, it has, a region here and a region here, right? So it's tracking which of our immediate children have users down below us in the region tree. Right, so effectively, this is tracking it, and you'll notice that this is actually a field mask set. So we're going to do a little digression here so I can tell you about this field mask set. But the way to think of this is that effectively this is a data structure that tracks, a set of things, and for each of those things, it associates them with a field mask. And well, what is a field mask? A field mask is just a representation of it's a bit mask representation of the fields that are set. So this will require just a little bit of digression here to explain this first, what a field mask is, and then what a field mask set is. But effectively, what we're going to get here is a set of open children and the list of the fields that they are open for. So let me actually show you just briefly. Let's do what a field mask is first, and then I'll tell you what this field mask set is, and then we'll be able to understand what that field state data structure is representing. So Legion has this bitmask class, which is just a generic set of bitmasks that are optimized with SSE and AVX and all sorts of vector intrinsics for different architectures and stuff. But there are lots of different classes of bitmasks in here. There's sort of a common bitmask, and there's AVX bitmasks, and if I can type correctly, well, I thought there was an AVX bitmask, but yeah. There are lots of different kinds of bitmasks in here for various different, there's the two-level bitmasks, here's the SSEs, and there's the AVX bitmask that I was looking for, and so forth. So there's lots of different kinds of bitmasks in here, but they all have the same interface. And what they do is they allow you to encode some information as a set of bits with an upper bound on the number of bits that you can represent in a mask. And in particular, what we do with Legion is we regularly represent, the sets of fields in a field space using these bit masks so that we can quickly test whether or not like two groups of fields are overlapping with each other, like whether two tasks, have region requirements that, are using overlapping sets of fields, right? Normally those are represented by a standard set of field IDs, which, you can intersect those, but it's kind of expensive to do that. Whereas it's much cheaper to do bitwise, bit comparison to see whether or not, there's any overlapping bits between the two bit masks, right? Hardware is pretty well optimized for doing that kind of optimization. And so, I'm coming back to region tree.h over here. If you actually look, we'll take a quick digression here into these field space nodes, but there's a way to convert, like your vector or your set of privilege IDs, into a field mask. And the way that Legion does this is it actually tracks, for every field ID in a field space, right? It has one of these field info things, and one of the field info things it has is a mapping onto an index and a bit mask, right? So every field in a field space, right, has a unique mapping onto an index in that bit mask. So if you have a field, you can just set that bit, right, and represent that in the bit mask. And this is why field spaces have an upper bound that Legion supports for the number of fields in a field space, right? Is effectively that we want to be able to easily encode how encode those fields in a bit mask like this. And so in order to do that, we need to have an upper bound on how many fields you can have inside of a field space, so we can say how many bits are in the bit mask, and then be able to do efficient operations on those bit masks and so forth, right? And what I'm not showing you here is, there's some special logic when you allocate fields to help make sure that you can get a unique index in that bit mask and so forth. And I'm not going to show you that today, but that code is there, and I can point you to that offline if you're curious. But that allows you effectively convert all the fields inside of a field space, to a particular ID and create a bit mask. Okay, so that's what a field mask is. Now let me show you what a field mask set is. So field mask set, this is in Legion utilities.h. This field mask set is a Legion class that we've defined that effectively allows you to create a set of pointer t's. So this says t, but you'll see like our actually encoding needs to be pointer t's, and then it associates for everything in this set. It'll associate a field mask with it, and it'll do that quite efficiently. And so what that allows you to do then is to iterate. You can think of this as like a map, really. I mean, it's called a field mask set, but it's really like a map where it's got a set of things in it, and for each of those things, it maps them to a particular bit mask, storing the fields that thing is set for, right? And if I actually show you the representation of this, you can see this thing has got like lots of operators or iterators and stuff like you would find in a normal C++ STL class. In fact, like its iterator interface is pretty much the same. Let's see, it's got lots of things that you would normally find in an STL set, like insert and erase and clear and sizes and swaps and getting iterators and stuff like that. So all the things you would normally find in an STL data structure. But you'll see, like, what we actually do is we actually represent this class. This class is optimized for the common case where there's only one thing in the set, and you have just a single field mask associated with that. But then, in the case where there are many things, we'll actually create an STL map, for all the things and associate a field mask with them. And in this case, this field mask here becomes a summary of all the fields that are set in this entire field mask set. So you can actually query like the summary of all the fields that are set in this field mask set with this method right here, which you'll see gets used quite a bit. So effectively, I'll save some of the details of how field mask sets and some examples of it to a little bit later. But effectively, the way to think of this is just this is a group of things that have a field mask associated with them, so telling you which fields are being used for those particular things. Okay, so now we can come back to this thing, right, which is our field state object, which has one of these field mask sets. I have a little type def here, for effectively defining our kind of thing, because it's really long once you put all the template parameters in there. But effectively what we have here is a list of all of our open children and the fields that they are open for, right? So like if I come back to my region tree here, right, we have a field state is storing the list of which children are open and which fields they are open for, right? So like not all children might be open for the same fields, right? And so that allows us to encode that in here quite efficiently, so we can know which of our children are being used by which fields. And there's actually another important thing in here, right, which is this open state member variable here, right? So open state is actually tracking the mode, quote unquote, of how those children are open. And if we actually look at what this open state is, I should actually probably move this enum over here into field state since it's pretty much only used over there. But there's really only five modes, or 5 states that you can be in. One is not open, right, which is, kind of obvious. In which case there won't be any children in this thing, and I don't even think we actually even use this anymore, so we should probably delete that one. But you could be open in a read-only mode where all of your children below for those particular fields are open in a read-only mode. They've only got tasks or other operations that are reading in that subtree. They could be open in a read-write mode where you've got tasks down below that are potentially writing. Doing writes and stuff. It could be open in a single reduce mode, which we'll talk a little bit about in a minute, and then also open in a multi-reduce mode. I'm going to show you the state machine for these things in just a little bit later, so we'll get into that. But effectively, there's ways to know which mode things are open in, and also in particular, if it is open in a reduction mode, we know the reduction op ID associated with what kind of reductions are being done in that subtree down below us. So we have all that information. Okay, so if we come back to register or to siphon interfering children, what you'll see is that what we're actually going to do is we're going to iterate over all these field states, right? So we can actually have multiple field states, right? In our logical state object here, we have a list of field states that describe all the children that are open and which mode they're open in, and which fields they're open for and stuff like that. And so what we want to do is like figure out which of those we need to close up, right? Well, so the first thing that we can do is actually check to see, like, when we're examining a field state, right? The first thing we do is we actually check to see, like, are there even any overlapping fields inside of this field state that we actually care about, right? So this is the set of fields that we're traversing for our particular logical analysis, right? This closing mask, right? And we can check to see if that overlaps with any of the fields. We've overloaded this operator star here to check for disjointness. So that'll actually check whether 2 bit masks have overlapping sets of fields, right? And that allows us to say, if there are no overlapping fields between these 2 sets, well, then there's not any fields that we care about, in this field state, for what we're trying to do. So we can just ignore it. We can just, go to the next one and continue and go back around the loop, right, and do the next one, right? So now if we get here, right, what that means is there's at least some overlapping fields, that we actually care about in this field state compared with, what we're trying to traverse for as part of our traversal, right? And so in that case, by the time we've gotten here, we effectively know that, like, there might be some interfering children, and they might be interfering, and they definitely have overlapping fields. So the next thing to check is, like, whether they're open in a mode that is consistent with what we're trying to do, or whether we need to close it because, like, the mode that their users down in that subtree might interfere with us, and therefore we need to go traverse it, right? And so what you see now is there's a big switch statement, and the switch statement will switch on this open state of the currently open subtrees, right? And what that does is, effectively, we're going to handle each of the 4 cases. There's the open read-only case, the open read-write case, the open single reduce case, and the open multi-reduce case, right? And for each of them, we're going to do something different, right? So let's just do a simple one first, and then I'll show you the state machine for what this looks like, because it's tedious to go through all the code for everything. But, for the read-only case, right, like, effectively, if we're also read-only, right, then what that means is that, we don't need to do anything with that subtree, because if we're reading and they're reading, even if we traversed it and we found interfering, or overlapping children down there wouldn't be any dependencies because we're both reading, right? So that's not going to cause us any trouble. We do a little check here to see if like we're open below, but in general, what you pay attention to is here's this part, which is like we don't do anything in this particular case because we know there's not any interfering stuff down there, right? However, if that tree is open in read-only mode, but we're doing something else, right? Like we're doing a write or a reduction or something like that. Well, then we need to close up that subtree and look for any overlapping stuff. So we call this perform close operations, which I won't show you right now. But effectively, it'll traverse down that subtree and look for any interfering children, that overlap with us on fields and privileges and other stuff like that, right? And then when we're done doing that, we check to see are there any remaining fields in this field state. If not, then we can remove it. Otherwise, we keep it in the list and keep going. So this will actually mutate this field state object as part of its closing stuff. It'll actually mutate this field state to remove out children that we've actually closed up completely. Like there are no remaining users down in that subtree because we recorded dependencies on them with our close op and so forth. Right. So there's actually let me actually show you the state machine for this for this the switch statement. So this is effectively the state machine, and you can actually see like this is actually like where we were in this first one, right? So we effectively doing read only. I haven't annotated where the close ops are. So like effectively, if we're in read only and we're doing a read the next time, right, we can stay in read only mode and everything kind of works out. But if we're writing or reducing, right, we're going to effectively have to do a close and then transition to a new open state, right? Like effectively create a new read write, open state, or in the case of reduce, we'd be the first reducer, so we go to this the single reduce state, right? And so this will show you the transition of these field state objects, as you're changing, what children are open and stuff as part of doing your traversal. Read write is also an interesting one because like effectively you can only have, you can have only one child open in read write mode if your children are interfering, right? So like if you're on this region and if you've got, one child open in read write mode and you're trying to traverse this child in read write mode, then you have to close this one and open this one. Interestingly, with partitions, you can have multiple children open in read write mode as long as those children are all disjoint. Like if you know that this is a disjoint partition, right, then you can have multiple children open in read write mode. Otherwise, if this is an alias partition, you could only have one child open in read write mode at a time, right? And effectively, if those children are open read write mode, then they kind of stay in that mode. Now, let me explain a little bit about what's going on with these single reduces and multi-reduces, right? So the first time that you open a child, right, like if let's say your tree is closed or maybe it was in read-only mode and now you're doing a reduction. So the first time you open a child with a reduction, we go into this single reduce mode. And the idea of the single reduce mode is effectively to detect the case where, if you're going to actually have like multiple things happening in the subtree, like multiple reductions of the same kind or different kinds, but all to the same child, well then in that case, we don't always want to do a close op. We might just want to transition, from a reduce mode to a read write mode, right? And what this means is the single reduce is saying there's only a single child open in this reduction mode, right? And so that allows us to optimize for the case of jumping to this read-write mode without having to do a close operation from performing a reduction, right? However, as soon as you have like more than one child open with a particular reduction mode, then we move to this multi-reduce node because like then there's no way to transition, over to this write without doing a close operation, right? Whereas here we can actually jump straight here without necessarily issuing a close op because we know we're going to traverse down the same, like the same child, and that allows us to kind of like skip a close operation in that particular case. So that's kind of like a little optimization. We could probably actually do away with that if we were willing to tolerate some additional close ops being generated, to close up a tree and then reopen it in a different mode. So the single reduce is effectively optimizing for that case, which tends to come up pretty frequently for things that are doing reductions. They often traverse like one child and then eventually do another child, or just do the same child but with different modes and stuff. And so we kind of disambiguate for those things. So one thing I like about this picture is that it actually is pretty similar to like a cache coherence diagram. So you can actually think of it that way. effectively, this kind of maintaining the coherence between the different modes, between subtrees and stuff, and making sure we're not doing anything that's interfering in any bad ways. So I'm pretty sure I've got this diagram right, but you guys might find a bug or two. But you can actually use this diagram to actually come back and look at the code over here, and what you'll see is that in this open read write case, we're often performing close operations, assuming that we're not traversing to the same child that's already open and stuff like that. And then here's the open single reduce case, right? And you can see there's sort of 4 different subcases here, which are reflected here in some of these things, like whether you have the same reduction op with a different child, or the same reduction op with the same child, or a different reduction op with the same child, or a different reduction op with a different child. Right, and describing all of those different cases, right? And then open multi-reduce is much simpler, right? Effectively, if you're using the same reduction mode, you get to have as many children open as you want, but as soon as you change reduction modes or do anything else, right, then you got to do a close op and sort of reset your state and stuff like that, right? And then effectively, if you get down here and you detected that you're not already open, there isn't already a field state to represent the child that you're going to traverse to, well, then you add in a new field state. You create a new field state, with whatever mode that you're going to be traversing that subtree with. You give it the set of fields that you're going to be traversing for, right? And you give it the child that you're about to be traversing, and then we stick that field state on this list of field states, right? So the next thing that comes along will actually find us, right, as a potential user down in a subtree that's potentially open, right? And so that adds us onto the back of the set. So, once we're done doing this traversal, we merge in all those new field states into the existing lists. And this is kind of a performance optimization where we'll actually look for field states that have the same the same open state. Right, it'll kind of collapse the same open state, both in state and read op, and then if so, it'll collapse the open children together to make sure that you only have one field state for each of the open state sort of conditions and stuff like that. Okay, so effectively this interfering or Ceph interfering children is effectively what's maintaining those those states of those different subtrees, so that we know which ones do we actually have to explore, right? This picture is a little bit simplistic in that you've only got 2 partitions, but there are often applications that make lots of partitions, right? And only a few of them get used by actual tasks and operations. Some of them are used to compute other partitions and things like that. And so you don't want to have to traverse all of them all the time. And by tracking which ones are actually open and actually have users in their subtrees, right, that allows us to only traverse the things that we actually need to, and only traverse the ones that have interfering coherent or privilege modes, right, that could potentially, interfere with the tasks that we're trying to actually use. Okay, so hopefully that actually explains Ceph interfering children and the state machine in a little bit more detail, so you can actually, see what's going on with that state machine. Okay, so let's jump back to register logical user here. Make sure I'm at the right one at the top. Okay, I think this is the right one. Yep. Okay, so after we've siphoned our interfering children, the next important thing, which I mentioned a little bit on the previous in the previous talk, but I want to go over in some more detail, is this perform dependence checks. And so if we actually look at the logical state class over here, so here's our logical state class. Right, so here's our field states that I showed you, that we effectively siphoned in the siphon interfering children call, right? And then the other important bit of state that we've got over here, right, are effectively these list of users. So these are the users, these logical user objects here, right, which are effectively, using this particular region in the region tree. So they've actually recorded themselves on a particular node on this region tree, whether it's, any of these nodes might have users recorded on them, right? And again, you'll see this, here's this field mask set thing again, right? And you'll notice this time, instead of storing the region tree nodes, right, which we're describing children, here we're describing logical user objects, right? And we're associating a field mask with each of them to say, which ones have which fields associated with them, right? And in particular, we have 2 lists here. We have the list of what we'll call current epic users, and then we have a list of the previous epic users. And I'll kind of describe why there's two different lists and what we could do. Or why we need those two lists as opposed to just having one list of all the users that are currently here at the moment, right? And so let's actually look at what happens when we actually analyze, look for interferences with the current users on this node in the region tree. So this is the point where we're actually looking to see, like, we're at a particular node in the region tree and see if there are any prior users using this node that we might interfere with, right? So the first thing we do is we actually do this check on the list of the current users, right? And imagine, let's actually assume for the moment that this is actually our only list, right? So to understand why there's two lists, let's actually imagine there's just one list for the moment, right? Well, we could go through and just analyze all the users in this list, right? And effectively record dependencies on all of them. And then, if we're done here, then we'll add ourselves to the list of users, here. And this list of users will continually grow, right, to accumulate all of the prior users on this particular node in the region tree, right? And that would be correct, right? But the problem with that is that list of users can then grow very large, right? Because effectively, that list might encompass everything back to the beginning of the actual execution of the program, right? And so we don't actually want to track all of those users. In fact, we don't actually need to track all those users. For example, if we have something like a write that comes along and dominates all of the prior users, and we know that everything that comes after that write will depend on that write operation, then we know there's a transitive dependence there, right? And so what that means is that you don't actually need to track all of the users. What you can do is you can actually do this sort of like two-stage tracking of sets of users, right? So as soon as some user comes along that records dependencies on everything in this current set of users, right, then those set of users can then become this previous set. And then the thing that dominated all of them becomes, the first thing in this current list, right? And when a new operation comes along, it'll check to see, like, does it interfere with something in this current list? Well, yes. Or if it doesn't dominate everything in this current list, then it will go and record dependencies on everything in the previous list, and that will be, give you all the transitive dependencies that you want. But if it dominates the current list, well then, this list becomes the new previous list, right? And the the new user becomes the first thing in the current epic set of users. Now, what I said is it works pretty well, except for in the case where you realize that there's lots of different fields running around, right? So you have to be a little careful here, and that you have to do this domination test not on literally all of the users, but you have to consider each field independently. Right, and so when we go look at this perform dependence checks, you'll notice that it returns a dominator field mask, which says which fields were dominated, meaning, like, did this user record, a dependence on all or did this, new user that we're analyzing record dependencies on all of the current epic users for those particular fields, right? And so you have to be a little careful to track that dominance of the granularity of fields, and not just like for everything in the list, because we actually have to be correct, you have to do that analysis individually on each of the different fields. So this perform dependence checks takes a Boolean parameter saying, or Boolean template parameter saying whether or not to track this dominance or not, right? And you notice you just check it when you're checking this current epic list, right? And then down here, when you handle the non-dominated fields, right, that's when you check the previous epic users. In that case, you don't have to check the dominance, because you're effectively gonna do the right thing right there, right? And so you effectively, and you can actually see when you get the dominator mask, right? Here's an example of some field mask arithmetic happening, right? You're effectively taking the mask that we were analyzing for this particular user, you're subtracting out the fields that were dominated, right? And that gives you the set of fields that were not dominated. And this double bang here, effectively, the bang operator will test to see if this set was empty, right? So effectively checking to see whether the set was empty. And so double bang means the set of fields here is non-empty, right? So you actually have to do this traversal. I've considered adding, effectively a Boolean operator to the field mask that will just implicitly convert it to a Boolean if it's not empty. But I haven't quite convinced myself that I want to do that, because it would be kind of hairy as to whether you use that correctly or not all the time. So I use this double bang operator to indicate not empty right now. Okay, so let's actually go look at this perform dependence checks method here to see, how it's tracking some of these things. Okay, so effectively we've got, here's the user that we're analyzing. Here's our ordered field mask users set, which comes from over here in Legion analysis. It's effectively a field mask set of all of our users, tracking their fields and stuff like that. Right, and here's the mask that we're checking this user for, right? And we're also, tracking there's some optimizations here for things about it below, and we've got the projection info and the state and other stuff. But effectively what this is going to do, let's see. I'll see if I can. There's some extra logic here for checking some of this, tracy and validate stuff, which not important to us today. One important thing that you can notice here. Here's one of those examples I showed you calling this like summary mask on the field mask set can be really effective, right? So if you actually have this set of previous users, you have if there's many things in here, you can actually get the summary of all the fields that are set, for all the things in this set by calling this get valid mask, right, on this set. And that tells you all the fields that are set for any of the users, right? And if you can say that like the mask that you're checking for is actually disjoint from all of the fields, for all the things, in this set, well, then you get to skip all the rest of this code. All these checks and stuff all go away because effectively that there's no overlapping fields with the thing that you're actually analyzing, right? So this is where that summary thing that I showed you on the field mask set can actually be really effective. You can actually easily check, is your mask non-interfering or non-overlapping with any of the fields in the set, right? And then you can quickly skip out of things by doing that. And so, if it's disjoint, then we get to skip. But if it's not disjoint, then we got to come in here and actually do all of these tests, right? Okay, so if we are not disjoint, let's assume we're not, because that's probably the more common case, right? Then we iterate over all of the previous users in the set, right? We have a little check here. It's not safe to record dependencies on, other operations or other region requirements from the same op, right? So effectively, there's a little check out for that. In fact, yeah. So if effectively if the previous user has the same, operation, the same index in the context, right? So this context index is effectively the, the order of operations in the parent task, right? And so if you're coming from the same operation, right, then you can skip that. And notice if we're tracking dominance, then effectively that field can no longer be considered dominated, right? Because like there's another user in here that we didn't interfere with. So we remove those set of fields from the dominator mask, which got set. We set the dominator mask to start with the check mask, but we gradually prune stuff out if we conclude that there's a user in here that we don't actually interfere with. Right, so the next thing that we do is we check to see, okay, this is a different operation. It came from a different thing in the same parent task. Right, check to see if the fields overlap with each other, right? And if they don't overlap, we just skip a whole bunch of stuff again, right? But if they do overlap, right, then we're going to come down here, right? If we're tracking dominance, we actually say, we actually observed. So one thing I'll say is it's not actually safe to know that you dominate something if you don't actually observe any users for particular masks. So we're actually tracking this observed mask to know whether or not we actually interfered with at least some user for some of those fields. So like as soon as you interfere with something, right, we'll track that observed mask here. So at this point, we effectively know we've got overlapping regions, we've got overlapping fields. The last thing that we can check is check to see whether there's any interfering privileges with themselves or interfering privileges between these two region requirements for these different users here. So that leads us to this check dependence type class or function. So let's actually go take a look at that. This is actually defined in Legion utilities.h. Let's see if we can find it. Check dependence type. So this is like one of the most important methods in Legion, because effectively what it's doing is it's checking to see, for two region usages, which, let me actually show you briefly what our region usage is here. Might be a struct. I thought it was in here. Maybe it's in Legion utilities. Let's see. Sorry. Region usage is right here. This is like a little summary struct for a region requirement. And effectively, it tracks three things, right? It tracks your privilege mode, your coherence mode, and your reduction operation ID if you've got one, right? And so this is like, that you can make one of these from a region requirement or just directly but it's a really simple class that just tracks these three things, right? And it looks to see whether those three things are interfering across between themselves, right? So this is the prior one, and this is the secondary one, right? So this is effectively checking to see, is there any interference between these two different kinds of region usage things, right? And so, if you're both reading, well, obviously there's no dependence there between those two things, right? So we can say that there's no dependence, right? We'll come back to this reductions interfere Boolean template parameter here, but probably in another lecture. But effectively, assuming reductions interfere, or sorry, assuming reductions don't interfere, which is the common case, right? Then if you can say that if they're both reducing, right, and both of them have the same reduction op, right, then you can immediately say, or then you can come down here and see, check the coherence modes, and as long as there's non-interfering coherence modes, right, then you can effectively say as long as they have the same coherence mode, then there's not going to be any interferences, right? If you've got mixed coherence modes where you're mixing exclusive and atomic stuff, right, then you do have to have a dependence here. But for most part, most things tend to use things with the same coherence mode, and so you don't get any dependence there. Otherwise, if you've got different reduction ops, well then there's obviously going to be a dependence between those two things, right? And then down here we've got checks for if everything is exclusive, right, then we're going to check, or if either of them are exclusive, then we're going to look for anti-dependencies. This check for anti-dependence method is actually right up here. It's just checking to see if there's like a write after read dependence, and if so, you get an anti-dependence. If not, then you'll get sort of whatever the default kind is here, which is a true dependence in this case. And then you get these other kinds of dependencies where, like, if you've got two things that are atomic, right, you can get an atomic dependence, and I'll say what that is in just a moment. And then similarly, like, if you've got other kinds of relaxed coherence modes, you can get simultaneous coherent or dependencies and so forth. And relaxed is still a little underspecified, but I think we know how we want to do that, but nobody really uses that today. So you can come in here and check, the states for all these different things and looking for understanding dependencies. But this will give us several different kinds of dependence modes, either a true dependence or an anti-dependence, or one of these atomic or simultaneous dependencies. Let me say briefly what these atomic and simultaneous dependencies are. Effectively, what they're saying is, like, we're not sure if there's going to be a dependence here or not. It's going to depend a little bit on the mapping, but for the purposes of the logical analysis, simultaneous and atomic dependencies both behave as if they are a true dependence, right? Effectively, it means that those tasks have to map in that order in order to figure out whether there may or may not be a dependence, during the actual, physical analysis or not. So you can think of, like, atomic dependence and simultaneous dependence as a kind of true dependence for the purposes of logical analysis, but then, that the dependence might go away during the physical analysis. So that's kind of what that is saying here in this analysis. So if we come back here to this check on these logical users, right? So we get this dependence type coming back from check dependence, and as we pass true for non-interfering reduction modes here. We look at this kind of dependence that we get back, and then we do different things depending on it, right? So if you get a node dependence, right, that immediately filters out from this dominator mask saying, like, we found a user that doesn't actually dominate, or that we don't actually dominate, so we're going to have to record ourselves in this same epoch, and then we're going to effectively need to also do the check on the previous users as part of that to make sure that we get all of our dependencies correct, right? And then effectively all the other kinds of dependencies all get treated the same way, with the exception of this validation stuff, which is for resilience, and you can safely ignore that. For purposes of correctness, this is all about tracking whether like whether regions have been validated and looked at by some later tasks for resilience and stuff. So you can skip that part. But everything else comes down here through these case statements. I'm going to skip this branch right here, which is all about control replication, and so you can safely ignore this for the time being. We'll talk about what happens with control replication in a bit, but effectively you get down here and you effectively at this point you record one of these region dependencies, right? And this will actually record a dependence between the prior, it'll take the user that we were analyzing and have its operation record a dependence on the operation that was part of the previous user, right? And that will, hook up a mapping dependence between those two operations to say like, this operation here is not allowed to map until this prior operation has mapped. If we have time, we will go dive into that. But it looks like we're probably going to run out of time today. So it loops through all these things and does this analysis for all the different users. I will point out this one little thing down here, which is this timeout case. So this timeout thing let me at least explain the sort of the really bad case that can occur, and it actually has occurred in practice, is sometimes users will actually do things like have a region which is like write once and then read only for the rest of like the like the rest of the application, right? So you write the region once, and then for the remainder of your code, you're just only ever reading this one field of the region or something like that, right? And the problem with that is that like even our like to list epic counting thing won't ever prune users out of the list, and so you can just accumulate more and more and more users in this list, right? And if that's the case, right, then this list can grow arbitrarily large. Like if you're running your application for a long time, and this list gets bigger and bigger and bigger, and it never gets smaller. So periodically, Legion actually has a timeout on the logical state. So if I find the logical state thing, let's see where to go. I'm in Legion analysis. Where did my logical state thing go? Oh, class logical state. Thought the timeout was in here. Maybe I am wrong. Let's see. Where is this timeout thing? Timeouts. I'm trying to remember where this timeout thing gets set. I can't remember, but we do have this list of timeouts. Or actually, so I remember. So sorry, it's on each of the logical users. So maybe it's struct logical user in here. There it is. Yeah. So and you see I even have this nice comment about it here. So effectively we have a timeout which says we effectively have some timer counter here, and I think it defaults to something large like 128 or something like that, or 256. Like effectively every 256 times that you do the check on this user, we decrement this timeout counter, and whenever it reaches 0, then we'll do this check over here to effectively see like has this operation been committed, right? And therefore we can prune it out of this list. And if you can do that, then you can actually remove it from the list, because the operation has actually already run all the way through the pipeline and committed itself. And so therefore, like anything that might need to depend on it, right, it's sort of trivially satisfied because the operation is already done running and is committed and done with itself. So you can prune it out of the list here, right? But you don't want to do that every time. It's expensive to do that. So like, we only do it every so many timeouts. But that handles the case to prevent this list from growing unbounded in the case where like you have a write once regen that's only read for the remainder of the application, and there are such applications that have such things. Okay, so one last thing I'll show you down here. I mentioned this track dominance stuff, right? So effectively, if we're tracking the dominance, right, then effectively what we do is so for writes, we have a special case here where we only want to check to see if we're writing, we know we're going to dominate everything, so we can effectively add ourselves into the observed mask if necessary, because we know writes, sort of trivially dominate everything that came before them. But for reads and reductions, you have to be a little bit more careful, right? And then what we do is, the actual set of dominated fields are the set of fields that are dominated, that were in the dominator mask and were also observed. Right, because like it's not safe to actually say, if you weren't writing, then it's not safe to say that that you dominate a field if you didn't actually observe dependence on any operations that came before you, right? And so you have to have this observed mask here also. And this, I'll say this ampersand here is doing exactly what you think it does on bitmask, which is doing a bitwise and like, so for example, this is a bitwise or equal. the bit masks. So this is all doing your sort of standard bit arithmetic kinds of operations, and those are all implemented like in SSE and AVX and other vector intrinsics inside of those bit masks. Okay, and so that gives you back the dominator mask. And so if we go back to register logical user, right, so we get back this dominator mask, right? Then we can compute the non-dominated mask by subtracting off from our user mask. And if we have any non-dominated fields, then we call perform dependence checks again, but this time, effectively doing the analysis on this set of previous epoch users instead of the current epoch users. And that'll do the check just for those fields, right? We don't have to do the check for all the fields anymore, just for the non-dominated fields at that point, right? And then after that, we can go through and do the rest of our logical analysis that we looked at the last time. So I think everything else I was thinking about doing today will take more time than we have left. So at this point, I'm happy to take any questions that folks might have about this. Yep. I'll put the picture of the state diagram back up here because it's probably the most interesting thing. No questions? All right. Well, if there's no questions, I'm happy to end a little bit early, give you guys some time back. So let's see. I think next week will be another Realm week. We'll be talking more about the DMA system, and hopefully we'll either be able to finish up logical analysis and move on to some other stuff in Legion in 2 weeks' time. All right. Thanks, and we'll see you guys next week.